continuation on power factor correction. So let me just change that. So we're still busy with the power factor correction. Right. So one of the methods of power factor correction, or one of the things that we employ when we are correcting the power factor, is we use a synchronous condensers. Right, so we use a synchronous condenser. Basically, by definition, a synchronous condenser is a synchronous motor that operates permanently at no load, and it is basically just used to improve the power factor. Remember, we said induction motors or induction loads have a negative power factor. So synchronous condensers or synchronous motors usually have a positive power factor. So we use them to basically correct the power factor or reduce the angle between the voltage and the current in our load, hence having a better power factor. So suppose we've got a load, just a normal load that has a negative or a poor power factor with a negative angle theta. So suppose your load is represented by this phasor diagram in this manner, right? So this would be, let's call this point A, point B, and point C. So this triangle ABC represents your basic load with a negative power factor, theta, let's call it theta 1, with a poor power factor. And we know that this here represents your P of the load. So that's the power or the real power of the load, which is given in kilowatts, right? And this here, AC, represents your apparent power of the load. Let's call it S1, right? And obviously BC would represent your Q value of the load, which we refer to as Q1, right? So we can see that this is a poor power factor, and I want to try and improve this power factor using a synchronous condenser. I'm saying synchronous condensers or synchronous motors are known to have a positive or a good power factor because they are synchronous loads, right? So you would then go ahead and you are given the power, suppose you are given the power of the motor and it's shown in this red line. So the tail of the power of that synchronous motor would be represented by that line there. So this here represents your PM, which is the power of that particular motor. You want to project this motor in such a way that it shows a positive power factor. So you can just go ahead and drag that line there down here. So this here represents, still it's the same, so it represents the power of the motor, meaning that the distance from here to there is equal to the distance from there to there. So let's call this point point D, and we call this point E. Right, so the motor or the synchronous condenser is known to have a positive power factor of a certain angle theta. So meaning that, oops, this is moving the wrong line. Okay, so from there to there, maybe this would represent the apparent power of my motor S at a positive power factor theta, and you call this power, this theta, we'll call it theta M. And obviously from that point down here, this would represent your reactive power Q of the motor. Right, so let's call this point A, B, C, D, E. Let's call this point F. Right, so now the red triangle CEF represents now the power diagram of our synchronous condenser. So we started a triangle ABC with a negative power factor, and we wanted to improve that particular power factor using a synchronous condenser that comes at an angle theta m, and it is a positive power factor represented in that particular manner, like that. So now we want to see how will this now help us to improve our power factor. So if you take now your pencil and you draw a line, say from this point A there to the point F. Now you have created a new triangle, which is the yellow one here. I'll just represent it in the dots like this. So that's the dotted triangle ADF. It's a new triangle with a resultant apparent power SR. So SR represents your resultant apparent power, which comes from the installation of that particular motor. And obviously, here you have a new angle, we call it theta R, which is your resultant power factor angle. So that means now I have improved this power factor of my initial load, which was the white triangle ABC, with the power factor theta 1, and I've improved it by adding this red triangle, or the power factor from the motor or my synchronous condenser triangle CEF, and I got now a new or a resultant or an improved power factor with triangle ADF and a new theta, which is theta R. So this is how we use our synchronous condenser when we want to improve the power factor of our system. So on the next section or on the next video, we'll do one example which is explaining this in detail.